solubility product. Solubility product. Solubility product means the product of polar concentrations of ions is said to be solubility product. For example, if we take AgNO3 solution, for this if we add NaCl solution, it will gives us AgCl plus NaNO3. This AgCl is precipitated out as a solid. Precipitation. Precipitation means when two liquids are mixed, from that mixture, because of such reactions, if certain solid is deposited while after mixing those two solutions, or two solutions which are in liquid state, if some solid is separated out, that we call it as a precipitate. So when precipitate is formed, for example, here AgCl is precipitated out. We are calling it as AgCl precipitate. AgCl precipitate means a solid which is separated when silver nitrate solution is mixed with NaCl solution is said to be AgCl precipitate. It means, in other words, this AgCl is not soluble, or we can say it is insoluble. Suppose, for example, if we take AgCl salt and NaCl salt separately, and if we added in the some water which was taken in a beaker, if we stir it, NaCl completely disappear after some time, whereas AgCl will be like that only. So we claim that it is insoluble in water. Though it is insoluble, whatever the salt it may be, there are so many precipitates, BaSO4, CaCO3, BaCO3, all sulfides of fourth group, they are precipitated. So such all precipitates, though they are seems to be insoluble in water, to certain extent they are soluble. Even this AgCl, when you dissolve in water, to certain extent it is soluble. So here the concentration of ions in water is very small extent. The concentration of ions is very small extent. It is a reversible reaction. So the product of the concentrations of these two ions, the product of the concentrations of these two ions is said to be solubility product, and it is known as KSP. It is known as KSP. That means here initial concentration is C. Initial concentration of these two are 0, 0. To small extent, let S, they are soluble. In such cases, if S moles of AgCl is soluble, S moles of Ag ions and S moles of Cl minus ions will be formed. Now at equilibrium state, the concentration of AgCl is C minus S, whereas Ag plus ions concentration is S and this concentration is S. If you write an equilibrium constant for this, you will write S into S by C minus S. When compared to C, the S is very small. So C minus S can be taken as constant or C. So this can be written as K into C is equal to S square. This K into C is known as KSP. It will be equal to S square. So for this type of salts, so if solubility is S, solubility product is S square. Solubility is S, solubility product will be S square. So there are so many types of salts we have. They can be classified as AB type. Now this is AB type, one anion, one cation. Second category is AB2 type or A to B type. Third category is important ones are A to B3. Like that, we will have different types of salts. So I'll give you some examples. So AB type means AgCl, BaSO4, CaSO4 or CaCO3, MgCO3. That means number of anions and cations irrespective of their charges. They are equal in number. Such salts are said to be AB type salts. A to B type salts. A to B type salts are cation is monovalent and cation is divalent and anion is monovalent. For example, CH3 AB2 type or MgS2, not MgS2. Cuprous sulfide, cuprous carbonate, like this. So it is A to B type, two cations with one anion, or MgCl2 or MgOH twice, like that. If anions are 2 and cations are 1, A3B3 means Fe2SO4 thrice, Al2SO4 thrice, like that. If you have, they are A to B type. So here, if we take this type of salts, they dissociate to A to B, dissociate to give 2A plus B minus 2. So if solubility is S, you will form 2S and S. So solubility product KSP can be written as 2S whole square into S. So it will be 4S cube. It will be 4S cube. So in such cases, KSP is equal to 4S cube, or S is equal to 4th root of KSP. S cube is equal to KSP by 4, or S is equal to cube root of KSP by 4. Sometimes they will give us solubility product and ask us to calculate solubility. In the previous case, KSP is equal to S square. So solubility S is equal to root of KSP simply for AB type. For A to B type or AB2 type, S is equal to cube root of KSP by 4. Cube root of KSP by 4. You have to calculate like that. For example, if you take Al2B3, A2B3 type salts, A2B3. So if it ionizes, it will gives us 2A plus 3 plus B 3B minus 2. So in such cases, solubility, if solubility is S, ions concentration is 2S and 3S. Then in such cases, KSP can be written as 2S whole square into 3S whole cube. 3S whole cube. So it will be 4S square into 3 3s are 9, 27S cube. So it will be 108 S to the power 5. So KSP is equal to 108 S to the power 5. So for such salts, solubility is equal to fifth root of solubility product by 108. Solubility. So another type is also there, AB3 type. In AB3 type salts, for example, FeCl3 like that, AB3 salts. For AB3 salts, they ionizes as A plus plus 3 B minus. If solubility is S, concentration of A plus ions is S and these ions is 3S. So for such salts, KSP is equal to S into 3S whole cube. That means S into 27S cube, or KSP is equal to 27S to the power 4. For such cases, solubility S is equal to fourth root of KSP by 27. So this is solubility product. Next, in this context, we have to learn another name known as common ion effect. Common ion effect. Common ion effect. Common ion effect means, we know, just now we discussed that each salt has capacity to dissolve to a certain extent. So the extent of solubility can be checked or controlled or decreased by adding a common ion, anion or cation, that present in that salt. For example, NaCl is soluble in water. Now if you want to decrease the solubility of NaCl, before adding NaCl to the solvent, if you add or if you increase the concentration of Cl minus ions or Na plus ions in that solution, the solubility of NaCl is decreases. For example, if you have taken certain amount of water in a container or a beaker. So in pure water, let's consider 25 grams of NaCl can dissolve. 25 grams of NaCl can dissolve. More than that, if you add more than that, it will be precipitated out. That means the concentration of NaCl, Na plus and Cl minus ions, when 25 grams of NaCl is added, so it is sufficient to present in the water. If excess of any one of that ion is present, the product will increases. The product will increases. For example, suppose in a given volume of water, if 0.5 moles of NaCl can be dissolved. In a given quantity of water, 0.5 moles of NaCl can be dissolved. In such case, if 0.5 moles of NaCl is soluble, then Na plus ions and Cl minus ions concentration in that solution will be 0.5 and 0.5 respectively. That means the solubility product is considered to be 0.25 moles square per liter square. That means if the concentration of Na plus and concentration of Cl minus exceeds this value, it will be precipitated out. It will be precipitated out. Up to that, it is soluble. Now, if you want to decrease the solubility, before adding NaCl, suppose if I add 0.5 moles of HCl solution to it, what happened? This HCl dissociate to give H plus ions and Cl minus ions. So now 0.25 moles of HCl is added. From that 0.25 moles of Cl minus ions are produced. Then I add 0.5 moles of NaCl. Now, here in such case, already 0.25 moles of Cl is there. So only 0.25 moles of NaCl will be soluble. Out of, even though if you add 0.5 moles, out of this, only 0.25 moles is soluble. Because already Cl minus ions, which are the common ion of NaCl, is already present in the water. Immediately after adding it, so before that only, this product will be exceeds 0.25. And not less than that only, because when total concentration of Na plus Cl minus and equal to this, then the solubility will be stopped. Not exactly 0.25, less than that concentration itself, it will be, the solubility will be stopped. That means only half of 0.25. That means 0.125 moles is soluble. Because of that, here you will get 0.125, 0.125. So that the product will become 0.25. By that way, we can decrease the solubility of a salt by adding a common ion which is present in the salt to that solvent. The solubility of the salt is decreased. This effect is called as solubility. This effect is called as common ion effect. Basing on that only, the cation group separation table was prepared so that the required cations only precipitated out according to the scheme. Because we are in the third group, you observe, we are going to add NH4Cl salt and NH4OH solution. In practicals, senior interlevel, you are going to do the practicals. In that practicals, we have three groups of cations. From third group, we have aluminium, ferrous, and ferric. In the fourth group, we have manganese, zinc, and nickel. In the fifth group, we have calcium, barium, and strontium. In sixth group, we have magnesium. Now, here, all these cations can be precipitated out as hydroxides if we add NH4OH to it. But to separate each one, what we are going to do, first we dissolve NH4Cl, which decreases the ionization of NH4OH, so that a little amount of hydroxides are sufficient, are evolved here, so that only these three can be separated out. Then we allow to pass this H2S, so that next these ions will be precipitated out. Then we change this with carbonates, and these ions can be separated out in the form of carbonates. So that group separation table is used or prepared basing on the principle of common ion effect.